Welcome everyone to the first episode of my new Unity tutorial series. I'm Gary House, and if you're new here, hit that subscribe button and turn on notifications so you don't miss out. This series is all about Unity's latest features, tips, and tricks, with a fresh tutorial dropping every few weeks. Today, we're kicking things off with Unity 6.2, hot off the presses, and we're building an epic afterburner effect for a jet engine using shader graph to create an unlit shader in HDRP. We'll also explore how Unity's built-in AI assistant can supercharge your workflow, from scripting flickering lights to generating custom audio. With that being said, let's blast off. Let's start with the scene overview. Here's the engine in action, thrust diamonds and shock waves in the exhaust stream. You can see the gradient from blue, hot core to orange flames, enhanced by post-processing effects like glow and color correction. From the side, check out the detailed engine model mounted on the test stand. The cone is emitting that intense, colorful exhaust, while post-processing adds the finishing touch. The shader drives the core visual impact, all running in real time in Unity 6.2 with HDRP. To understand the foundation, let's jump into Modo for a quick look at the thrust cone asset. I modeled this simple cone shape here. It's elongated for that jet exhaust feel, with a tapered end, and includes ring shapes internally arrayed along the exhaust stream. UVs are unwrapped along the length for seamless texture scrolling, which is key for our shader's animation. I applied a basic color gradient from blue at the base to red at the tip. As this is a hero shot, and this is HDRP running on a desktop, I wasn't overly concerned with poly counts. Now back to Unity. I have already created our shader graph, and the material to be assigned to the thruster geometry. We will start on the right side of the shader graph and focus on the graph inspector. This is where we set our shader parameters that drive the associated material. First, I set the material type to unlit, surface type to transparent, and blending mode to additive. Then near the bottom of the graph inspector, I enable distortion, setting a distortion blend mode to add, and then toggle on distortion depth test. Now, all the way on the left, in our blackboard, we will focus on the 10 exposed properties I set up. I added the following exposed properties, so they can be tweaked in the editor. Main color strength, color saturation amount, Fresnel strength color, emissive saturation amount, emissive color, emission strength, Fresnel strength emissive, distortion tiling, and distortion speed. You can see their different types, such as texture 2D, and the rest are floats. Now let's walk through the shader graph and highlight each node. Moving to the first section, the Vertex offset noise group. Start with the position node, which is set to object space, providing the vertex position. This feeds into an add node. Also feeding into the add node, there is a time node. This controls animation. That is then multiplied by our distortion speed property. And then this is fed into a simple noise node, with its scale set to 500. You should experiment with different values here or add another exposed property so that it can be changed in the editor. Next, that simple noise is fed into another multiply node, as well as our property distortion tiling. From there, another multiply is added, and a normal vector node set to world space is fed into the same multiply node. Next, a position node is connected to an add node, as well as a previous multiply node. Finally, this result goes into the vertex offset input, warping the mesh subtly. Next, let's take a look at the color group. Start with the Fresnel effect node. Connected to its power attribute is our Fresnel strength color property for edge translucency. Directly underneath our Fresnel effect is our sample texture 2D. This is driven by our exposed property main color. This allows us to plug in any texture we want in the editor's inspector. The output of both the Fresnel effect and the sample 2D texture are fed to a multiply node to control color and Fresnel. Then we have our exposed property main color strength multiplied by the previous multiply node. This is then set to the base color of the fragment section of our shader, completing control of the color of the exhaust. Now the emission group. The setup here is very similar to the color group previously showcased, starting with the Fresnel strength emissive property from the blackboard and connected to a Fresnel effect node's input. Then we add the emissive color property from the blackboard and connect that to a sample texture 2D node. Next, both the Fresnel effect node and the sample texture 2D node are connected to a multiply node. The output of this multiply node is connected to the B slot of yet another multiply node. The A slot of this multiply node has the emission strength property from the blackboard connected to its A slot. This multiply node is connected to the in slot of a saturation node, and the saturation value is controlled by the property emissive strength amount from our blackboard. This result connects to the emission control of the fragment. Finally, the distortion texture group. It begins with a time node. Then we have two multiply nodes. The time is plugged into both A slots of the multiply nodes, and the distortion speed property is connected to both multiply nodes' B slots. These are then combined using a vector 2 node, which all this feeds into the offset slot of the tiling and offset node. By doing this, we control the animation offset of the texture for animating the distortion. Next, we add a sample texture 2D and plug in a normal map noise into the texture slot. Next, I multiply the sample texture node by some values. You will need to set these values based on your particular needs, or create a float and expose it. Then the output of that is connected to the B slot of an add node. The A slot of the add node is fed by a screen position node. The add node is connected to a scene color node to pick up the background. Then we multiply that output with an exposure node. This node is needed in HDRP so that the geometry correctly responds to lighting exposure. The output of this last multiply node is connected to the distortion attribute of the fragment. That's the shader. Apply the material that was already created alongside the shader graph to the thrust cone mesh. Tweak the properties in the inspector and watch it ignite. But what's an afterburner without dynamic lighting? I wanted real-time lights inside the cone to flicker and cast rays into the scene, simulating plasma instability. That's where Unity 6.2's AI assistant shines. I prompted it to generate a C# script for a point light that flickers in intensity between a minimum and a maximum. I also added an overall light intensity so I could animate its intensity while keeping the flicker. The AI delivered a robust HDRP solution, and here's how it works. The script, named Flickering Light HDRP, includes public variables for min EV100 intensity and max EV100 intensity, as well as flicker speed. The script converts EV100 to lumens for HDRP compatibility. Finally, audio. No thruster is complete without that roar. In the AI menu, I selected Generate New and then selected Sound. It generates a new audio clip that I could rename. Then I tweaked the prompt until I got what I wanted. It was then attached to the dynamic point light and set to loop, then made adjustments to the audio clip's playback settings. And there you have it. The Afterburner is ready to rock. Feel free to comment and leave questions. I'll do my best to respond. Stay tuned for the next tutorial, and if you feel up to it, hit the like and subscribe, and let me know what Unity features you want covered. Thanks for watching, and see you again soon.